What if the universe was hiding something so strange, so extreme, that even light itself couldn't escape it? Something invisible, silent, but powerful enough to rip stars apart, bend time, and swallow everything that crosses its path. These mysterious giants aren't science fiction. They're real. And they're called black holes. But what is a black hole, really? Is it a hole in space? A portal? A cosmic vacuum cleaner? Let's clear things up. A black hole is not an object in the traditional sense. It's a region of space where matter has collapsed into an incredibly small volume, creating a gravitational field so intense that nothing, not even light, can get out. It forms a kind of invisible trap in the fabric of space-time itself. If something crosses its edge, known as the event horizon, it's gone for good. No signal, no return, no escape. At the center of a black hole is what scientists call a singularity, a point of infinite density where the known laws of physics no longer apply. Time and space, as we understand them, essentially cease to exist. Black holes are nature's ultimate paradox. We can't see them directly, but we can see their influence. They warp space, stretch time, and pull in matter like nothing else in the universe. So how do these monsters form? Where do they come from? And what happens if you fall into one? To answer that, we need to go back to the death of a star. To understand how a black hole is born, we need to look at the life and death of a star. Stars, like our sun, shine because they're constantly balancing two forces: the inward pull of gravity and the outward push from nuclear fusion in their core. For millions, even billions, of years, this balance holds. But eventually, every star runs out of fuel. When a massive star, at least 20 times the mass of our sun, reaches the end of its life, fusion stops. And without that outward pressure, gravity wins. The star collapses in on itself in a violent implosion. Its outer layers explode outward in one of the most powerful events in the universe, a supernova. What's left behind is the core, so dense, so compact, that space itself curves around it until a black hole is formed. This is how most stellar mass black holes are born. But not all black holes form the same way. Some come from the collision of two incredibly dense objects called neutron stars. These crashes send ripples through space-time, called gravitational waves, and sometimes leave a black hole behind. Others may have formed in the early universe, just moments after the Big Bang. These are known as primordial black holes, hypothetical, but still a topic of serious research. And then, there are supermassive black holes, millions or even billions of times heavier than our sun. Strangely, we find one at the center of almost every galaxy, including our own, the Milky Way. But how they formed? That remains one of the biggest mysteries in astrophysics. One thing is clear: black holes are not rare. In fact, our galaxy alone may contain millions of them, silent, invisible, drifting through space. But once formed, what exactly is a black hole made of? What lies beyond that mysterious boundary we call the event horizon? Let's take a closer look. So, what exactly is a black hole made of? Surprisingly, it has no solid surface, no structure in the traditional sense. But scientists define its anatomy using three key parts: the singularity, the event horizon, and the accretion disk. Let's start at the center. The singularity is where all the black hole's mass is concentrated into a single point. It's a region of infinite density, where gravity becomes infinite, and space and time as we know them break down. In reality, we don't know exactly what happens here. Our physics simply stops working. Surrounding the singularity is the event horizon, the invisible boundary that marks the point of no return. Once anything crosses this threshold, whether it's a spaceship, a star, or even light, it can never escape. It's not a physical barrier, but a gravitational limit. Outside the event horizon, escape is still possible. But inside, there's no turning back. Around many black holes, especially those actively consuming matter, we often find an accretion disk. This is a spinning disk of gas, dust, and stellar debris spiraling toward the black hole. As it gets pulled in, this material heats up to millions of degrees, emitting X-rays and other forms of energy. That's why, even though black holes themselves are invisible, we can see the chaos around them. In fact, the first image of a black hole, captured in 2019, was actually a glowing accretion disk surrounding the dark shadow of the event horizon. And there's one more strange feature: gravitational lensing. Black holes bend light around them so strongly that they can distort the view of stars and galaxies behind them, almost like a funhouse mirror in space. So while a black hole may seem simple, just gravity gone wild, it's actually a complex, layered phenomenon that challenges everything we know about the universe. But not all black holes are the same. Some are the size of cities, others the size of entire solar systems. Let's explore the different types of black holes next. Not all black holes are created equal. In fact, astronomers classify black holes into three main types, based on their size and mass: stellar, intermediate, and supermassive. 1. Stellar mass black holes. These are the most common. They form when massive stars die in supernova explosions, leaving behind a core that collapses under its own gravity. A typical stellar black hole weighs between 3 to 20 times the mass of our Sun. Despite their immense mass, they're only about the size of a city, maybe 30 kilometers across. There could be millions of these stellar mass black holes in our galaxy alone. But since they're invisible unless actively feeding, most go undetected. 2. Intermediate mass black holes. For decades, these were the missing link. Too massive to be stellar black holes, but too small to be supermassive. Intermediate black holes are believed to have masses between 100 to 100,000 solar masses. They may form when several smaller black holes merge, or from dense star clusters collapsing under gravity. In 2020, astronomers detected gravitational waves from what appears to be the merger of two black holes, creating one around 142 solar masses, a strong candidate for this rare category. Still, direct evidence is limited, and scientists are actively searching for more. 3. Supermassive black holes. These are the giants. Found at the centers of nearly all large galaxies, including our own Milky Way, they have masses ranging from millions to billions of times the Sun. The one at the heart of the Milky Way is called Sagittarius A*, and it has a mass of about 4 million suns. How these monsters form is still a mystery. Did they grow slowly by feeding on matter over billions of years? Or were they born massive during the chaotic early moments of the universe? Whatever the answer, supermassive black holes shape the galaxies around them. They regulate star formation, emit powerful jets, and influence the structure of the cosmos on a grand scale. So from tiny collapsed stars to cosmic behemoths billions of times heavier than the Sun, black holes come in many forms, each more fascinating than the last. But no matter the size, they all share one terrifying feature: once you cross their edge, you're not coming back. Next, we'll dive deeper into that very boundary, the event horizon and the mystery of the singularity. The most iconic and mysterious parts of a black hole are the event horizon and the singularity, two concepts that stretch our understanding of physics to its limits. Event horizon, the point of no return. The event horizon is the outer boundary of a black hole. It's not a physical surface, but a mathematical boundary, an invisible sphere where gravity becomes so strong that escape is impossible. Imagine falling toward a black hole. From far away, you'd accelerate, feeling the pull. But the moment you cross the event horizon, you're doomed. Nothing you do can stop your descent. Not rockets. Not signals. Not even light can escape. From the outside, time appears to freeze at the event horizon. To a distant observer, you'd seem to slow down and fade away, never quite crossing the edge. But from your point of view, you fall in normally and fast. This strange warping of time and space is a direct consequence of Einstein's theory of general relativity. Singularity, where physics breaks down. Deep inside the event horizon lies the singularity, a one-dimensional point where matter is crushed to infinite density. All the mass of the black hole is packed into this tiny, unimaginably dense region. Here, space and time don't behave like they do elsewhere. The gravitational pull becomes infinite. And the known laws of physics? They stop working. We can't describe the singularity using our current understanding of science. Quantum mechanics and general relativity, two pillars of modern physics, don't agree on what happens there. That's why many scientists believe that understanding the singularity could unlock a theory of quantum gravity, or even deeper truths about the fabric of reality. But for now, the singularity remains hidden, shielded behind the event horizon, beyond our reach, beyond our sight. And yet, black holes aren't just destructive voids. They stretch time, bend space, and even affect how we experience reality itself. Let's talk about one of the strangest consequences of black holes: time dilation. Black holes don't just bend space, they bend time itself. And this isn't science fiction. It's a real consequence of Einstein's theory of general relativity. What is time dilation? According to relativity, time doesn't tick at the same rate everywhere in the universe. The stronger the gravity, the slower time passes. Near a black hole, gravity is so intense that time slows down dramatically. This phenomenon is called gravitational time dilation. In fact, the closer you get to the event horizon, the more time stretches. For someone orbiting just outside the black hole, only a few hours might pass, while years go by for someone far away. This isn't theoretical. It was visualized in the movie Interstellar, and while Hollywood took some liberties, the science behind the concept is solid. Time travel? Sort of. So does this mean black holes are time machines? In a way, yes. Falling into a black hole doesn't let you travel back in time, but under the right conditions, extreme gravitational fields could allow for one-way time travel into the future. For example, if you spent a few hours near the event horizon and returned to Earth, you might find that decades or centuries had passed here. This kind of forward time travel is entirely consistent with the laws of physics. Extreme clocks in space. In fact, GPS satellites must already account for time dilation. Because they're farther from Earth's gravity, their clocks run slightly faster than clocks on the ground. Without this correction, GPS systems would drift by kilometers every day. Now imagine a place where the time difference is not milliseconds, but years. Time itself bends in the presence of a black hole. But if you get too close, not only would time stretch, you'd also be stretched. Literally. Let's explore what happens if you fall into a black hole, in a process scientists call spaghettification. So what would actually happen if you fell into a black hole? First of all, it depends on the type of black hole. A small, stellar mass black hole would kill you quickly. A supermassive black hole? Surprisingly, you might not even notice crossing the event horizon, at least not right away. The tidal force of gravity. As you fall in, gravity doesn't pull equally on all parts of your body. The gravitational pull on your feet would be stronger than on your head, stretching you out. This effect is called tidal force, and in extreme cases, it becomes so intense that you're stretched into a long, thin strand, like spaghetti. Scientists call this horrifying, but kind of funny sounding, fate, spaghettification. Your atoms get torn apart, then your subatomic particles, and eventually, even information about you might vanish forever, or so we thought. Quick death or gentle drift. In a stellar black hole, this would happen outside the event horizon. You'd be torn apart before you even crossed the boundary. But with a supermassive black hole, the tidal forces near the event horizon are weaker. You could actually pass through the horizon unharmed, only to be crushed later, closer to the singularity. No matter what, there's no way out. Once you cross the event horizon, your fate is sealed. What happens after? What happens to your information? Is it lost forever inside the black hole? This is one of the biggest debates in modern physics, called the black hole information paradox. Some theories suggest that information is somehow preserved. Others say it's destroyed forever. Stephen Hawking even changed his mind about it. Either way, falling into a black hole is not a trip you'd survive. But it might teach the universe something about the very nature of reality. And ironically, over time, even black holes themselves don't last forever. They evaporate. Next, let's explore one of Stephen Hawking's most mind-blowing ideas, Hawking radiation. For a long time, scientists believed that nothing could escape a black hole, not even light. But in the 1970s, Stephen Hawking challenged that idea with a radical new theory. He proposed that black holes aren't entirely black. In fact, they might glow, very faintly, by emitting something called Hawking radiation. How can a black hole lose energy? According to quantum physics, even the vacuum of space isn't truly empty. It's constantly bubbling with virtual particles, pairs of matter and antimatter that pop into existence and annihilate each other in a fraction of a second. But near a black hole's event horizon, something strange can happen. If one particle falls into the black hole while the other escapes, the black hole loses a tiny bit of its mass. This escaping particle becomes real radiation, slowly draining energy from the black hole. This is Hawking radiation. And over trillions of years, it could cause a black hole to shrink and eventually evaporate completely. The end of a black hole. For small black holes, this process would happen faster. As the black hole shrinks, the radiation increases, creating a runaway effect until it eventually ends in a powerful burst of energy. For supermassive black holes, this evaporation would take longer than the current age of the universe. So even though black holes seem eternal, they die, just very, very slowly. Does Hawking radiation solve the information paradox? Maybe. Maybe not. Some scientists believe Hawking radiation might carry information away from the black hole, solving the paradox. Others think that new physics is needed to fully explain what's going on. What's clear is that black holes are not just cosmic vacuum cleaners. They're dynamic, quantum objects, bridging the gap between gravity and particle physics. But if black holes are so hard to detect, how do we even know they're real? Let's take a look at the observational evidence that proves they exist. Black holes are, by their very nature, invisible. They emit no light. No image of a black hole can show what's inside the event horizon. So, how do we know they exist? The answer: we see their effects on matter, light, and even space-time itself. Watching stars orbit the invisible. One of the best examples is at the center of our galaxy. For decades, astronomers have tracked the motion of stars near a mysterious, invisible object called Sagittarius A star. These stars whip around at incredible speeds, in tight, elliptical orbits, some taking just 16 years to complete a loop. The only explanation? A supermassive black hole, millions of times the mass of our Sun, packed into a region smaller than our solar system. And we can't see it, but we can watch everything orbiting it. X-ray and radio signals from feeding black holes. When black holes feed, pulling in gas, dust, or even entire stars, they generate intense heat and radiation. As this matter spirals in, it forms an accretion disk that glows with X-rays, which telescopes like NASA's Chandra X-ray Observatory can detect. These emissions let us locate and study black holes, especially stellar mass ones in binary systems, where they orbit a visible star. The first real image of a black hole. In 2019, the world saw something historic. The first ever image of a black hole shadow, captured by the Event Horizon Telescope, EHT. The blurry orange ring showed the supermassive black hole at the center of Galaxy M87, 55 million light-years away. What we saw wasn't the black hole itself, but the glowing gas and light around it, warped by extreme gravity. This was direct visual proof that black holes aren't just theoretical, they're real. Gravitational waves, listening to collisions. In 2015, scientists made another breakthrough. They detected gravitational waves, ripples in spacetime caused by two black holes colliding. These waves confirmed a century-old prediction by Einstein and opened a new window into the universe. With instruments like LIGO and Virgo, we now hear black holes merging and can even estimate their mass and spin. So no, we can't see black holes with our eyes. But with telescopes, radiation detectors, and gravitational wave observatories, we're learning more about them every day. Now let's take a step back and ask, where did all of this begin? Could black holes have formed in the earliest moments of the universe? Not all black holes are born from dying stars. In fact, some may have existed since the very beginning of the universe. These are called primordial black holes, and they could be older than galaxies, maybe even older than the atoms in your body. Formed in the chaos of the Big Bang. Just after the Big Bang, the universe was a swirling soup of energy, particles, and radiation. It was hot, dense, and expanding rapidly. In that chaos, some regions might have had slightly higher densities. If those fluctuations were intense enough, they could have collapsed in on themselves, forming tiny black holes. These primordial black holes wouldn't need stars to form. Some might be the size of atoms, yet with the mass of a mountain. Others could be as massive as planets, or more. Do they still exist today? We haven't found direct evidence for primordial black holes yet, but they remain a compelling mystery. Some scientists even propose that they could make up a portion of dark matter, the invisible material that holds galaxies together, but which we still don't fully understand. If that's true, the universe could be teeming with ancient black holes we've never seen. How are we searching for them? Astronomers are using gravitational lensing, cosmic background studies, and even gravitational wave data to search for signs. If we find them, it could not only explain the nature of dark matter, but also give us a glimpse into the conditions of the early universe, just fractions of a second after the Big Bang. Primordial black holes, if they exist, are ancient time capsules. They may be whispering secrets about the universe's first moments, waiting for us to learn how to listen. In this journey, we've traveled from the edge of space-time to the heart of gravity itself. But black holes aren't just cosmic monsters. They may hold the key to uniting quantum mechanics and general relativity, and answering some of the deepest questions in physics. Let's bring it all together in our final conclusion. Black holes are some of the most mysterious and extreme objects in the universe. They defy our intuitions, break our models, and challenge the limits of what we think is possible. What we've learned. We've learned that black holes form from the collapse of massive stars, that they come in different sizes, from stellar to supermassive, that time slows near them, and falling in means no return. We've seen how they warp space-time, generate powerful radiation, and even emit energy via Hawking radiation, slowly dying over trillions of years. We've explored theories about primordial black holes, and how they might even hold the secrets to dark matter and the early universe. And we've seen how, despite being invisible, we know they exist, thanks to cutting-edge science and technology. Why black holes matter to science. Black holes aren't just astronomical oddities. They are natural laboratories for testing our understanding of physics. At the center of a black hole, general relativity breaks down. Time and space collapse into a point. It's here that we face the greatest unanswered question in science. How do we unify gravity with quantum mechanics? Whatever the answer is, it likely lies beyond the event horizon. A cosmic mirror. In a strange way, black holes are like mirrors. They reflect not light, but our own curiosity, our hunger to understand the unknown. They show us the power of observation, of math, of imagination, and of daring to ask, what lies beyond? The more we study black holes, the more we realize they don't just change our understanding of the universe. They change how we see ourselves in it. And that's why black holes matter.